introduction. Hello, everybody. I'm Seth. We pronounce it Weidman. Technically, from the German, it should be Weidman, but my family always pronounces it Weidman, so Seth Weidman. I'm a senior data scientist at Metis. Metis is a data science training company. So what that means is I teach our full-time data science immersive programs, which are kind of like boot camps, but we're accredited and have a couple other things in there. And also do corporate training, where we go into companies and teach their employees about data science. So first, just want to get a little pulse of the room. So who here knows what machine learning is? Raise your hand. Okay, good, good. Who here is a machine learning practitioner who uses machine learning on a daily or frequent basis? Okay, not as many, that's okay, good. I think that there'll be some interesting stuff in here for you, for sure. Who here knows what neural nets are? Okay, cool. And who here is like a neural net practitioner? There aren't really that many of them. Anybody? Okay, we have one. Excellent, excellent. Cool. So, Metis, we have this conference coming up called Demystifying Data Science. And my passion, what I'm interested in, is sort of demystifying neural nets and machine learning. And making this stuff, making you understand what's actually going on, because there's a lot of hype and buzzwords floating around up there. And as I think you'll see, I had a lot of fun putting this presentation together, so I hope you have fun. All right, so the agenda. What are neural nets, and how are they connected to the rest of machine learning? And the theme that we're running throughout, should we be scared of them? Why do they work? Okay, we know they work, they can do these cool things, but why do they work? Well, the answer is just math. There's actually a couple more things, but mostly math. And then, what are the latest advances in neural nets? What are some of the really cool, mind-blowing things that neural nets have been able to do? And should we be scared of them? All right, let's get into it. So machine learning is like this, right? It's AI, scary, computers learning how to do things on their own, and it's going to take over the world, right? Well, not exactly. So I asked my students, just the data science bootcamp students at Metis, what is the goal of machine learning? And they gave some great examples. I'm sure many people here would give. Finding patterns in data was something they said a lot. I would argue the goal of almost all machine learning is to mimic human intuition at scale. So what does that mean? Like a simple example, Amazon, right? You go on Amazon, you buy a book. Let's say you bought Moby Dick. And what could Amazon do? Well, they could have a bunch of people that sit around and say, you like Moby Dick, here are some other books you would like. They could hire a bunch of librarians. Or they could use machine learning to try to essentially get close to that librarian's performance, but do it automatically, do it using code. At Trunk Club, if somebody buys a pretty conservative white shirt, you want to recommend to them something like conservative dark jeans. You wouldn't want to recommend them something super flashy. So machine learning is just a way to do that at scale. All right. A huge myth about machine learning is that it's like this, is that it's people sitting in a room like John Nash in a beautiful mind, coming up with these brilliant algorithms and figuring out what's going on. It's actually it's more like this. It's a process that involves taking lots of data and usually relatively simple algorithms and putting these together in clever ways so that you can get predictions which hopefully can get close to mimicking human performance on tasks like recommending books based on past books you bought. So it's a process that involves feeding lots of data through relatively simple algorithms. It doesn't necessarily involve complex math and computers learning things on their own and so on. And I think many of us know this, where does machine learning work well? Meaning, I would argue, where can it mimic human performance? Well, it's typically good with data sets that have few relevant features relative to the total number of data points in your data set. There are ways around this. You can use PCA and dimensionality reduction to group features together, but most of the time it works well in these contexts. And this works extremely well for many business applications, which is why tons of businesses use it, but it fails sometimes when we try to get to these more human tasks. For example, image classification, right? I think Many of you are probably familiar with this kind of reasoning. Image classification, if you want to determine whether an image is of a cat or a dog, and you want a computer program to do that, it has to look at every pixel, and every pixel is a feature, and it has to decide for each one of those pixels, how much does that pixel influence the probability of the image being a cat or a dog. There's just a lot of relevant features. I mean, if a 32 by 32 image, it has over 1,000 features. So traditional machine learning techniques break down. Nevertheless, neural nets, and this is a key point, neural nets are really just an extension of these traditional machine learning techniques that are used for the same thing in just for slightly different problems. So what are they in the framework we've sort of set up? Neural nets are a class of algorithms, right? Before we had data and algorithms, that's sort of how machine learning works. Neural nets are just a different type of algorithm, serving the same purpose as other machine learning algorithms, designed to mimic human performance at scale. Again, same purpose as the prior algorithms we've gone over, on more human tasks, tasks with high dimensionality that have a lot of features that are relevant to the problem. So tasks that it works really well on that I'm sure at least some people are familiar with. Image classification, neural nets have blown traditional machine learning techniques out of the water. Language translation, and even you might have seen these cool examples of writing in a particular style. A neural net can read all the essays by a particular author and learn how to write in that style of that author. And even though neural nets, to sort of demystify them, serve the same purpose as machine learning in a lot of cases, and training them is similar, the results have been staggering. I don't want to downplay that. So in 2007, on the classic cats and dogs problem, a cutting edge result, a result that blew away anything that had come before, was that was a classifier that was 82.7% accurate. It could take in an image, and it got, of all the images it got, half were cats and half were dogs. So 82.7% of the time, it could figure out whether the image was of a cat or a dog. That was in 2007. Now, using open source tools, using just tutorials you can find online, and an intermediate level knowledge of neural nets and Python, any Metis data science immersive graduate could build a classifier with 95% accuracy, easily. And if you hire the smartest machine learning people in the world and use bleeding edge computers, and you have people that work at companies like Uptake and other places, they can get this up to 98% accuracy. But fundamentally, so neural nets, just the advancements of neural nets have blown these traditional techniques out of the water. And similar results have been seen in like language translation. So I'm sure a lot of people in this room maybe are data science managers or work with data scientists and need to understand, what it is they do all day, and what and essentially like what they're spending their time on. So I think it's important to make this point, that the lines of code needed to do machine learning and neural nets, it sort of breaks down like this. Actually doing the algorithms part of machine learning is maybe 10 to 20 lines of code. It's not that challenging. There's open source libraries you can import, and you can build a model that's very good using very little code. Actually cleaning and prepping the data takes 10 times as long, takes much longer. And actually deploying the model and having it work broadly takes even longer than that, takes about twice as long as that. With neural nets, building the model can take significantly longer than it can for machine learning. There's just a lot more knobs you can tune with neural nets. But still, there are plenty of tutorials out there, and there are libraries that are constantly reducing this number, making it easier and easier to build deep neural nets. I had a student in this cohort who built a deep neural net in TensorFlow with like 10 lines of code. You just sort of say, this layer has this many neurons, this one has this many, this one has this many, and that's your neural net. But the point is, neural nets are a little more complicated in terms of building the model, but even with neural nets, building the model is not the hard part. Cleaning and prepping the data and deploying the model and having it work broadly is the hard part. I will say, though, that in terms of the knowledge and expertise you need, it's very easy to screw up the building the model part. You do need a fairly high level of math and stats and machine learning expertise in order to do that. We've all experienced and heard of stories of companies deploying models into production that ended up not working as the data scientists who built them thought they would. This is very common. And the probability of, or the possibility of screwing things up is even higher with neural nets. So this is sort of where you need a data scientist to come in and have their expertise shine. With the rest of this stuff, this is where the sort of line between data science and software engineering gets blurry. Typically, some companies, the data scientist work would stop here, and the rest of this would be handled by software engineers. But at other companies, data scientists might do all of this. So this is sort of software engineering type work down here. All right. Okay, so let's get into the math. So how do neural nets work mathematically, or how are they trained? Just at a really high level. Oh yeah, well first, so neural nets, right, are these complicated, mysterious AI systems. They learn on their own, and they're just like mysterious, and we don't know how they work? Not really, not exactly. They actually work because of high school calculus. Yeah, there we go. I know, right? Easy. So, high level, how do neural nets work? Well, if you have a neural net that's trying to detect cats versus dogs, the neural net sees examples.
We still need satisfied.
It makes predictions based on seeing those examples. So it gets an image of a cat and it says, what's the probability that this image is a cat versus a dog? And then it figures out how much it missed by. This is really the key step. It says, okay, I got an image of a cat. The probability of this image being a cat in reality is 1. It is a cat. My neural net predicted that this image has a 70% probability of being a cat. So I missed by 0.3. And then the neural nets use this miss. They use the 0.3 to update each of those weights in the neural net. And by the way, I skimmed over this, but you can think of a neural net as a really complicated mathematical function that has a bunch of weights. So a bunch of parameters, just like linear regression has maybe 10 parameters or whatever, if you have 10 variables. Neural nets can have, common neural nets can have thousands of parameters, and the most complicated neural nets can have millions of parameters. But they're just these complicated functions that have a bunch of parameters, and there's a bunch of interdependency between the parameters based on how the functions are linked together and all that stuff. And I'm skimming over this now, but you could spend an entire 4 to 6 week course just on this part of this slide. But for now, you can just think of neural nets as being complicated functions that have a bunch of parameters. There's a subtle but important point to make here, which is this. It's commonly thought that neural nets learn by seeing lots of examples. And that's mostly true. Neural nets really learn when, after they've seen an example, they sort of reflect and say, how much did I miss by? Well, I thought the image was a 70% probability of being a cat, but it was actually 1, or it was actually 0. And they really learn when they do this reflection process. The algorithm is called backpropagation, but it's really a sort of process of reflection. And this is kind of like, this kind of mimics, I think, how humans learn. So how many of you have been at a party and you've met someone and they've told you their name and you've immediately forgotten it? Anybody? Anybody? Has that ever happened to anybody in this room? I've got 2 hands up here. If Borko never remembers anybody's name.
What's your name?
Exactly.
Thank you. All right.
Yeah. I would argue this happens because of the following. And neural nets learn by just repeating this process with more examples. I would argue this happens because of the following. And this is a famous quote on learning from John Dewey that I really like. We don't learn from experience. We learn from reflecting on experience. You don't actually learn someone's name when they tell you their name. You learn someone's name when they go, okay, Borko, got it, your name is Borko. When you take that time to reflect, that's when you actually learn. If you're reading a book, how many times has somebody read a book? You're reading a book and you read a paragraph and you get to the end of the paragraph and you have no idea what you just read, right? you know, it's a little bit of a myth that you can learn just by reading. You have to reflect. You have to read and then say, okay, so this, okay, got it. That's how we actually learn. We don't learn from experience. We learn from reflecting on experience. And I think neural nets are the same. All right, back to neural nets, the actual math. Okay, so what actually happens? We do that process I described on the prior slide. And for each step, for each example we pass through the neural net, we do the following. For each individual weight in the neural net, each one of those thousands or millions of little parameters, we adjust it. We adjust it a little bit so that, and remember, for each example, we computed the miss. We computed how much the neural net missed. For each one of those little weights, we compute how much that miss contributed to the, how much that weight contributed to the miss. And then, this is the only slide in the deck with calculus, but we compute the partial derivative of this miss with respect to, partial derivative of the weights with respect to the miss, and then we update each individual weight so that, using this equation, which I'll review on the next slide, so that in the next iteration, the neural net will hopefully miss by less. And many of you may know that neural nets involve a lot of matrix computations in order to do them, and that's why they run faster on GPUs. The only reason for that is that in order to compute this for every weight in the neural network, there is the sort of clever and fast way of doing that involves a lot of matrix multiplications. That's it. The reason that neural nets have matrix multiplications is in order to compute this partial derivative. You also do matrix multiplications on the forward pass, but you do them on the backward pass to compute this partial derivative. All right, why does that equation make sense? This is gradient descent, for those of you that are familiar with gradient descent, but for those of you that aren't, I'll walk through this because I think it's a subtle point that is often missed. So let's suppose that increasing one of those individual weights, we take one of those weights and we increase it, and what comes out the other side is that our loss increases. Well, that means we need to decrease the value of that weight. And that's exactly what this equation will do, because the partial derivative of the weights with respect to the miss will be positive, and so you'll be subtracting a positive number from that weight. Scenario 2 is we increase the weight a little bit, and lo and behold, that actually decreases our miss. Well, that's great. Let's keep going. Let's keep increasing that weight. That's what we want to do. And that's exactly what the above equation will do, since the partial derivative of the weight with respect to the miss will be a negative number. And so we'll be subtracting a negative number from that weight, and we'll be increasing the value of that weight. That's really the math of how neural nets work. I was talking to a couple people at the Toyota Institute of Technology down at U of C, and like, I was asking him, like, do you get to learn about more of the theory of neural nets and all that? And he's like, it's just the chain rule, it's just partial derivatives. So yeah, and all the matrix multiplications that make that work are just in order for each weight to get adjusted by a certain amount in the right direction during each pass of the neural net. Now I mentioned that neural nets are trained sort of in the same way as machine learning, and that is true. But there's one other component that really in the whole neural net ecosystem has made it work, and that's GPUs, which are they're specialized processors that can do parallel computations really well, and matrix multiplications are sort of infinitely parallelizable, as it turns out. So that's why GPUs are used to make neural nets run faster. But it's the same process. Feed lots of data through a neural net. Ultimately, you hope you're going to get predictions that mimic human performance. The process for training neural nets is simple and identical in concept to that of machine learning. So let's get back. Oh yeah, and first, are the cutting edge results doing anything different? What about convolutional neural nets that are used for image classification, where you have deeper layers and not every neuron is connected to every other neuron in the next layer? Or recurrent neural nets with LSTM cells, which are used for language translation. These cutting edge frameworks are just extensions, discovered mostly by trial and error, of the basic framework described previously, and they work in the same way. You show a neural net examples, oops. You show a neural net examples, you have it miss, and then you have the neural net repeatedly update its weights based on misses. And And that's all how neural nets work. Now, should we be scared? Let's return to that question briefly. All right, Newsweek. How Facebook's AI bots learn their own language and how to lie. I hate that we're eavesdropping in on her conversation. I feel bad. Yeah. We should start replying to her and see if she. All right. So, no, Facebook did this just by training neural nets using the process that we described before. The difference was that they used reinforcement learning to train their neural nets, meaning they trained them using penalties and rewards instead of losses. So they were training their neural nets in a negotiation setting. They were trying to train their neural nets on how to negotiate. And the neural nets learned a strategy when they were talking to each other that wouldn't work with humans. They learned that to propose that I will make you an offer of 5, they would actually just say the word the 5 times, right? It's like a thing that a machine would understand but wouldn't make sense to a human. That's it. So in other words, there were these things that humans trained that sort of learned a strategy for communicating with each other that was different than the strategy they would use to communicate with a human. Well, that sounds to me kind of like this. Now, those dogs are playing together, they're communicating with each other. Note, though, that the one dog is really like eating the face of the other dog. It's eating its face. So you wouldn't do that with a human. This is exactly what happened with Facebook's neural nets. They learned a strategy to communicate with each other that was different than what they would use with a human. But again, these are just things that have been trained by humans. I mean, dogs are wolves, right? Like they're just trained by humans to be domesticated. The difference between the Facebook situation and this is that neural nets are trained to mimic human performance on specific tasks, whereas dogs are just trained to be cute and good companions. And that's what neural nets are used for, and that's why they're merely a natural extension of machine learning. So before I move on, did you have a question?
No, I thought that when they repeat the same thing 5 times, that was discovered by John Belushi when he said cheeseburger, cheeseburger, cheeseburger.
Yes, exactly. That's true. It's true. You could train a neural net to talk like John Belushi. It might have been that they were they were watching Blues Brothers. No, they were watching Saturday Night Live. Excuse me, that wasn't Blues Brothers.
It's a winner.
Exactly. There you go. All right. There's one big exception to this, though, and it's a huge cutting-edge neural net result. And it's what I'm going to focus on for the rest of the presentation. All right. Tell me what you guys see.
Picture.
Yeah, picture. This little projector's a little blurry. These are pictures of bedrooms. They look real to you? Any of these look fake?
The one on the right.
The one on the right, this one looks fake?
Yeah.
Looks fake? Top one? Maybe these 2 are fake? And the rest are real?
I refuse to answer the question.
They're all fake. They were all generated by a neural net program that learned how to generate images that look like bedrooms. Let's get into how that happens. So the year is 2014. Ian Goodfellow, a graduate student at the University of Montreal, studying under Joshua Bengio, a leading researcher in the area of neural nets. And he wondered, can we train a neural net that is designed to trick other neural nets by generating fake images that another neural net will think are real? Interesting. He had the following idea, and this gets pretty complicated, but we're going to walk through it. Oh no, first just a preamble. So neural nets, you have its structure. The weights for the neural net are updated using this equation. And at the end of this update, you have what is mathematically a gradient, but what I'll call a residue, which represents how much each input feature to the neural net contributed to that neural net's prediction.
And
Right, makes sense. How much does each input contribute to the prediction?
The pretesting I agree with that.
All right. So his idea was this. you start out with this feature vector. It's just a vector that you can feed into a neural net. And this vector goes through a neural net and spits out a random image. It initially starts out, it's random noise. That random noise image is fed into another neural net. And that other neural net makes a prediction that says prediction. And it compares the prediction that it made to an actual value of 0 to compute the loss. Because this is a fake image. This neural net is going to try to detect real from fake images. So it compares the prediction that it made to an actual value of 0. The researcher says, this is a fake image, the real value is 0. That's that. Thank you, by the way. I'm not done yet.
But it's so good.
Thank you, thank you. Okay, but we're not even at the good part. All right. Then, based on the researcher saying, okay, this is a fake image, we're comparing the prediction of this neural net to a value of 0, you get a loss. And you use this loss to update the weights of this second net. So this net is going to get really good at saying that fake images are fake. Oh, I pressed the wrong button. That's okay. There we go. Let's review. Generate a fake image. We go to the second neural net. It computes a prediction and compares it to a value of 0, which the researcher says is 0 because it's a fake image. We compute the loss, and we use the loss to update the weights of the second net. Now, the second net produces its residue, which says, for all those pixels that first net gave me, for all those pixels of that fake image, I know how much each of those pixels contributed to that prediction that I made about whether this net was real or not. And the really clever thing is you can use this residue and the prediction that this second net generated, which says, what is the probability of this image being real? We can use those two pieces of information to update the weights of the first net. So the first net's going to say, okay, I give you a fake image, and you said there was a 10% chance it was real. Next time I give you an image, you're going to say there's an 11% chance it's real. Next time I give you an image, there's going to be a 12% chance it's real, then 13, etc. But there's a problem with this. This is only, by the way, part 1. The problem with this is the second net is going to get really good at detecting fake images, at saying fake images are fake. We also need to make this net smarter and make it know that real images are real. So we actually train that using the typical way you train neural nets. We give it real images of cats, of bedrooms, whatever. Put those images through the neural net. And we make predictions using this neural net, this time comparing the predictions that we make to the actual value of 1. Because these are real images, and we want this neural net to know this is real. So you need to know which is real and which is fake. This is real. Then, compute a loss, and use that loss to update the second net. So the second net will also learn how to learn what a real image is, basically. All right, some of you are probably familiar with this process, so I'm going to do some terminology. This is this thing I've been calling the first net, which takes in vectors, just random vectors, and generates images. We call this net the generator. And the second net, what I've been calling the second net, which takes in images and says, you're fake, you're real, you're real, you're fake, you're real, is called the discriminator. This entire process, most generally, is known as adversarial training, is an example of adversarial training, I should say. And this process in particular, with these structure of neural nets, is called generative adversarial networks, or GANs. And to give you an intuitive idea of how this works, I'll give you a quote from the original paper on GANs by Ian Goodfellow himself. The generative model can be thought of as analogous to a team of counterfeiters trying to produce fake currency and use it without detection, while the discriminative model is analogous to the police trying to detect the counterfeit currency. Competition in this game drives both teams to improve their methods until the counterfeits are indistinguishable from the real articles. And Jan LeCun, who is the director of AI research at Facebook, the inventor of convolutional neural nets, the inventor of them, in 2016 on Quora said that GANs and the variations that are now being proposed are the most interesting idea in the last 10 years in machine learning, in my opinion. Let's look at some more results from these. And one key point that has sort of been running throughout, but I want to make is it's not just the algorithms themselves that are driving these cutting edge results. It's the combination of algorithms, really fast GPUs, fast computers, because these things take a long time to train, which, you know, a long time is equivalent to just lots of computing power. I mean, you need lots of examples. And large data sets, which universities and companies like Google and Microsoft are compiling and then publishing and making open source so researchers can use them. All right. That said, what I'm going to show you now are some faces generated by GANs. And they get kind of weird, I'm not going to lie. So I just want to warn everybody. Some of them get kind of weird. These examples were not picked because they were the best examples. These are actually random examples of images that were generated by GANs, of faces. So here we go. All generated by a computer program trained by a human that had learned how to generate, that had learned what a human face looks like. Some of them aren't so good, some of them are really good, but I think it's remarkable when you step back and look at this one, for example, which is probably the best of these 5. This is not an actual person that exists in the world. This is a fake face generated by a computer program that has learned what humans look like. What human face, what a 32 by 32 image of a human face looks like. That's not a real person. Might look like someone you know, but it's not. What's next? Okay, some more really cool results. It turns out, and this is a kind of a cherry-picked result. Researchers highlighted in their paper, but it's a little more cherry-picked. It turns out you can take those initial vectors that generate these faces and add and subtract them to modify images. And it's really hard to describe, but I'll just show you an example. Here's a fake image of a smiling woman. If you subtract off the vector that generated an image of a neutral woman and add in the vector that generated an image of a neutral man, what should the result look like? Smiling man. Smiling man. That's the result. So you can do arithmetic on faces. You could add 2 people's faces. I don't know. Whatever. It's wild stuff. So now I want to go through a couple examples that show some really interesting data sets that have been compiled and what the cutting edge results people are getting out of these data sets. So here's a data set, the Carnegie Mellon Multi-Perspective or Multi-PIE database. A bunch of researchers took 750,000 images of 337 people, recorded in 4 sessions over 5 months, and they took them of different perspectives. So those are the images of the faces, but they took images of people, so they took an image of someone from this perspective, from this perspective, from this perspective, etc. So what can you do with that? Well, researchers had the following idea. They could take an image like that, and they could train GANs on the following. They can train GANs to say, given an image of somebody facing this way, the GAN can learn the relationship between somebody's face facing this way and somebody's face head on. So the following image was generated by a computer that has learned how to rotate faces. Not bad. And this is the actual image of the guy. So again, this was not a photograph. This was generated by a GAN.
It looks better as generated.
What?
Looks better when it's generated.
Looks better as generated. One of the students said it's a little bit hard to see, but they dropped his unibrow a little bit. He has a unibrow in real life, but not in the GAN. So yes. Here's another really cool data set, deep fashion. bunch of researchers at looks like the Chinese University of Hong Kong, as well as some Asian think tanks and companies, got 800,000 images, richly annotated with massive attributes, with clothing landmarks, and all this really cool stuff. And let me show you like an example of the things that are in this data set. So they have, for each image, they have where all the different joints on her body, where her left elbow is, where her hip, her shoulder, her neck, etc. are. In addition, they have all the landmark, the attributes of the clothes, where the bottom of her skirt is, where her waist, the belt is, etc. And here's a really cool visualization. This showed for a bunch of images in the data set where all the left elbows appear in that image. So you can see that most of the blue ones are the left elbows. So most of the time, the left elbows are on the left side of the image, right, as you'd expect. Sometimes the person's turned around, so the left elbow is actually on the other side. And this is where all the left sleeves are in the image. They're on the left side, as you could expect. Some are up here because the person's doing that, or whatever. Sometimes they're over on the right because they've turned around, or maybe they're doing this, etc. So they have people in all these different poses. What have researchers done with this? Well, they can take images like this, of a model on a white background, modeling some clothes, and they can give her a pose. They can say, take this image and take this pose and generate an image of this person in this pose. And you'll see in this pose, she's actually sort of turned around because the image that was generated, and this was not a cherry-picked result, by the way. They showed a ton of results, and I randomly chose this one. The image that was generated was that. And then researchers, this is actually a fairly well-known thing. You could use neural nets to sharpen images. That's you feed a GAN or another neural net, actually just a bunch of blurry images and sharp images, and it will learn how to sharpen images. So it sharpened the image to this. That was the sort of final result. Versus, that was the actual photo. Not bad. What's wrong? What's missing though? Straps. Drop straps. So it's not perfect, but still. And what actually impressed me even more, because this is a sort of pristine image on a white background, etc. What impressed me even more was that this works in the wild. Here's just a photo of a woman on the street wearing a backpack. We give her this pose, and the result is this. And sharpening that up, we get this. These are not real photographs, generated by a computer. Versus the actual image, this. In real life, it doesn't work as well. It works extremely well, but we miss her backpack. We lost her backpack. We lost her bike. It looks like she might have a bike. It's unclear from the image, etc. Really cool stuff. So, back to the original question. Should we be scared of this? I think there is some really potentially troubling stuff here. So you could imagine a future where, like, if we say, oh, I'm accusing you of a crime, and you say, but I wasn't there at that place, they say, but we have a photo of you pointing a thing at this, And humans can already do that. Humans can Photoshop things and manipulate pixels and all that. But I think with this technology, there's the potential to do that at scale. We could say, oh, you have a video of this politician with shaking hands with this guy in a dark alley, right? And we have a video, we have thousands of photos of him doing this and meeting with the Russian whatever, etc. And it's
a lot of fake news.
Yeah, a lot of fake news. Well, yeah, it's interesting stuff. I think another interesting thing is if you would have asked philosophers outside of the field maybe 5 years ago, what are the potentially troubling uses of AI you foresee in the future? I don't think anybody would have foreseen this. This GANs result has completely taken the entire field by storm, and nobody really expected it. So how should we think about AI? Well, there was a quote just last week by a man, Vladimir Putin, who says, "The nation that rules AI will rule the world. The nation that leads an AI will rule the world." And I mean, I actually literally had a conversation with a friend just before this, where I said, and this is definitely what I believe, that if World War III ever happens, it will be won by the nation with the best hackers, for sure. I think these tools, AI tools, unlike, say, guns or nuclear weapons, they're not really harmful by themselves. I mean, you're taking images of someone and like rotating them. I mean, who cares, right? But I think we, as sort of people in this field and just educated people in general, should be aware of these techniques. We should be aware that they're out there. But we shouldn't be scared of the tools themselves, because ultimately, it's the people who use the tools, not the tools themselves, that are really what we should keep an eye on. Thanks, everybody. Question? Yeah, this was. This is a joke I stole from my co-instructor. He said you should say, they actually took a photo of the back of my head and then used a GAN to generate that. It's amazing. It's amazing.
Seth, given some of what you just closed with there, would you see, potential, legislative type of restrictions, somewhere on the horizon about what these technologies can be used and not used?
A couple of things. First, it's very hard to regulate software, as we're seeing with cryptocurrency. There's really no way that governments could regulate that. Governments all around the world would have to act in concert, and that's really hard to do because of the way the internet is. But secondarily, I don't think it should be regulated because of what I talked about. Like, AI is sort of harmless in itself. You're taking, what are you going to do? Prevent a researcher from like writing a program that generates faces? I think it's more like the public should have awareness that these tools exist, that fake photos will become a thing, and we should be ready for them. I think obviously what happened in the 2016 election, it's the FBI and everybody has corroborated that the Russians put out a lot of fake news and stuff. We will never know and won't comment on whether Trump would have won the election anyway. We'll never know that. Nobody will ever know that. But I think it caught everyone off guard because people weren't aware that that kind of thing could happen. That a bunch of hackers could put out a bunch of fake news, spread it all over Facebook, and potentially change people's minds. So I think it's more that we just need awareness about this stuff, that this is possible now. Yeah.
Does this also work like when you add time? So when you show like 5-year-old after that would work like it will be like.
It absolutely should if you have training data. So researchers would have to, and probably someone working on this, would have to just get photos of people at age 5, people at age 15. And if they had enough training data, absolutely. Good question. Yeah.
I have a question about the reflective process you described, the backward propagation.
Yes.
Does that adjust the weights so that the error is 0? Or is there an incremental approach to the weight adjustment?
It's just an incremental approach. Yeah. You'll never get to 0. Yeah, just because the real world's too messy. Yes, Sarah.
I think there still must be some policy-related regulations, right? Like, for instance, because of this Equifax event, everyone says, oh, someone is going to get a mortgage on your name. I mean, I kind of ask myself, why should I worry about that, but not the bank who gives the mortgage? You see what I mean? If I really ask money from you,
Yeah.
it is your decision to give or not to give.
Yeah.
And now suddenly I think we turn the world around. Now I have to worry about that nobody is going to really ask for mortgage, especially in a world where we can really fake everything.
Mm.
You see what I mean? I think in that sense there got to be some regulations so
Yeah.
that safeguards are placed at the right places. Like as a person, what kind of control I have to prevent someone, right,
Yeah.
from getting a mortgage. I froze all my accounts, but people still say it is not enough. But,
Yeah.
I mean, what can I do?
Nothing.
Exactly. So in that sense, I think regulations say then really it is the bank that
Yeah.
must be
But
the
it's easy to say,
gatekeeper.
it's easy to say that somebody should have a regulation. I mean, I think this is one of the points, the things that's so messy and there's so many things.
Exactly.
Well, so it's easy to say, oh, the government should take care of that. The government is not gonna, take care of 5% of anything. So, I mean, there's just too many things. So I think, what seems to be changing, at least from my perceptions, we're changing an attitude of just toward information. It's not that we used to trust everything, see a picture, oh, there it is, there it is, that has changed. Something has changed in the last few years, if not in the last year, and I don't know exactly what it is, but I'm sorry to talk so much.
Sorry. Another point is that I think actually these are going beyond human capabilities.
Yeah.
I mean, can you imagine these robots trading in a matter of microseconds? Humans will never be able to do that.
Mhm.
You
That's
see what
true.
I mean?
Yeah.
So in that sense, I think maybe there is some reason to think about, like, really, I mean,
Yeah.
where should be the limit? Like maybe a group of people, nature is not a machine. It's a
Mhm.
group of people, right, who can have
There's another
capability
question
of
here.
that nature.
Yeah. I think we had a question over here
Yeah.
too.
So in your view, what do you think are good applications for using neural nets?
Well, there's many.
Yeah.
There's lots of people using them for time series applications. I'd say, so first of all, yeah, at a high level, many of these things you might say, okay, well, so what? Like, how would a business use this, or what's the application? It's a great question. There are many techniques that have been developed for these almost like toy or play examples that are now being used for more like business applications. And one is using recurrent neural nets for time series prediction. So traditional time series methods, they'll decompose things into a trend versus a cycle and use moving average models and other things. But recurrent neural nets, which were originally developed for language translation and things like that, are now being used for time series modeling. So there's just many examples like that where advanced techniques are now being applied to like simple problems and improving on those traditional techniques. Yeah.
So you said you're using advanced techniques for simple problems.
Mhm.
So there's
Simple probably isn't the right, probably like traditional problems that classical stats previously.
And
had tackled.
then, so using recurrent neural networks for time series will give you, it's expected that it'll give you better results?
I think
than-
here's a good concrete example. I just read a blog post that the Uber engineering team posted where they found that a model based on recurrent neural nets and what are called LSTM cells beat traditional time series methods at predicting demand, which is Uber's whole business, right? They're trying to predict demand so they can do surge pricing. So yeah, some people have found it. I think it's an important point to make, and this might be what you're thinking of, that you definitely should not just apply these techniques willy-nilly to any problem just because they're cool advanced techniques. But in certain situations, yeah, people have found that they beat like traditional stats, more traditional stats methods.
We did something like that
Yeah.
with a PhD student at Bell Labs, and we also used recurrent neural networks with LSTM, and it actually out-predicted ARIMA by about 8%. So it's not a
Interesting.
whole lot, but 8%
Yep.
is still 8%.
Yeah, I think the Uber blog post
In a
was
business sense, that's
a
huge.
naive
Yeah.
approach would have gotten them 13%, an advanced time series approach would have gotten them 9% error, and then the neural network got them 5 or 6%, so it's a significant.
Does it generalize though?
Yeah, it did, across various data sets for IoT devices.
More technical question
Sure.
going back to these weights.
Absolutely.
Do you adjust them one at a time, or is there interaction, or how do you?
Yeah.
How do you account for interaction between
You
weights?
can, in theory, do whatever you want. The traditional way that most people do it is they update all the weights in the network at once on one pass. In theory, you could do something where every time through the network, every time it sees an example, you only update half the weights. And then the next time through, you update another half of the weights. But yeah, typically people update all the weights every pass using that equation. It's a great question. Yeah.
Just trying to visualize what the raw data
Mhm.
traditionally we think of, you know, 1 row per person or.
Yeah.
This is, so let's say you have like 30 JPEGs of
Yeah.
people or stuff, like, I'm just trying
Here's
to
what it
imagine
is.
what it is.
An image, so, two things. First, the thing that goes into the generator network to generate the fake images is actually just a vector, random vector of length 100. And the generator network learns how to take any random vector and generate an image that is of the same class as the real images. Now, where do you get your the real images, which is probably what you're
Right, that's what I'm trying
thinking
to-
about, is, so imagine you have 32 by 32 pixels images. So you have 1,024 features. And in most cases, you actually have 1,024 times 3 features because you have the R, G, and B values for every pixel. So every image is 3,072 columns. The R value for pixel 1, 1. The B value for pixel 1, 1. The G value, etc. And 3,000, and that's the data. So that's why you need neural networks as opposed to, say, logistic regression.
Right, because it's like, that's a massive amount, like
Yeah.
7 JPEGs, which is to be a massive amount of data.
Yeah, I mean, these are working with, you know, hundreds of thousands. Yeah.
How important is the location, sort of the centering of the image
Mm.
or?
Those kind of things?
Yeah.
Yeah, it turns out not that important because of the way convolutional neural nets work. They detect different features sort of wherever they are in the image, and then they'll figure out if there's a, like for cats and dogs, if there's a nose in the image, regardless of where it is. And yeah.
So there's sort of an element of feature extraction from the images themselves and then a level of comparing that to.
I think the way you should think about it is the neural nets are doing the feature extraction within the neural net. Like you're just feeding, so this is getting slightly off topic, and I'm not an expert in this, but essentially what neural nets have disrupted, to use the tech industry term, is researchers used to take images of cats and dogs and do all these manual feature extraction. Is there a curve here? Is there a nose there? Is there an eye? And they would manually figure all that out, and that's how they got to 82.7% accuracy. Convolutional neural nets are doing all that for you. They're learning which features, and then features of features, and then features of features of features are important in the neural net, and they're just learning all that. So you, the human, don't have to do any feature extraction. The neural net is doing the feature extraction itself. Yeah.
You mentioned the large amount of very expensive computer time
Right.
that was needed. Who are some of the companies that are making the best of these computers?
Well, the way, for example, most people do it is they actually rent computing space and time in the cloud. What that means is you go up, the most popular one by far is Amazon Web Services, or AWS, as everyone knows it. So I can go on my laptop right now and rent a bleeding edge supercomputer on AWS for, I don't know, something really expensive, $50 an hour, $100 an hour. And I could run neural nets and train GANs extremely fast on that computer. So the answer is, I don't know, most people just have Apple laptops and then connect to AWS or Amazon. But Google also has a Google Cloud platform, but Amazon's is by far the biggest. Yeah.
Can you get these things to tell you how they're working, this to say back out what's going on underneath all of this?
A lot of people are working on that and working on ways to visualize what is going on inside neural nets. And the answer is it's not easy. It takes a lot of work, but yes, people are working on that. And yeah, there are ways, but it's not like easy. That's the short answer.
The major barrier is that there are just so many ways.
The major barrier
is that there are just so many parameters that no human mind can retain at all and actually deal with them.
Yeah.
Logistic regression.
Right. It's you know, logistic regression, there are 10 parameters and maybe 5 of them are important. Here there might be 10,000 parameters, and like 7,000 of them actually matter. Like you would need to interpret all 7,000 to figure out what's going on, and that's the reality. Yeah.
Just making this real, is there a tie to us, our brains, from a neural net perspective, and how do we stack up against a neural net? What kind of neural net
I
would
think
have to?
to answer and to address a little bit of what Sema was saying earlier, like with generative adversarial networks, humans can, using Photoshop and animation technologies, produce faces that look real. They can't do it fast. Just like Amazon, if I said I like Moby Dick, people in this room could recommend books to me way better than Amazon could, but they can't do it in microseconds, and they can't do it at scale. So
But
I think
one of the things you're doing
yeah.
with that is you're focusing the attention of the neural net on a specific topic. We're able to process everything.
Can they generate? I think that's actually a really important point, is that, to my knowledge, people are working on this like mad, but to my knowledge, an architecture that has learned to classify images won't be able to learn how to translate languages. And I'm almost hesitating saying that because there are a lot of people working on this, and somebody might have come up with that, but that's the dream, is that you train one neural net and it knows how to classify images, knows how to generate faces, and it knows how to, that's like Google's dream, right? Or I don't know, researchers at Stanford, that's their dream.
Maybe Watson can do it.
What?
Watson?
Watson, yeah, no, probably not. But
In future.
yeah, there's a good article about how Watson's basically just smoke and mirrors, a lot of it. Yeah, look that up. Watson is yeah. Anyway.
Excuse me, would you repeat that, the article?
Oh yeah. It was in Statistics News or something like that.
What was the thrust of it?
The thrust of it was Watson is being used to detect cancer, and it's just not, and it's not doing nearly as good of a job as IBM advertised that it should have done.
Oh.
And people that are in the field know this. IBM is sort of they just spend a ton of marketing to try to push Watson out there, but the technology is not very good.
Okay.
Sorry. Anyway.
One more question, please. Will your slide be on your website?
Yes, I'll, why not? Yeah. Thank you for reminding me.
Seth has agreed that we can post it on the website and make that available. Thank you. You know what? I don't know that we could have started out this year's series with a more relevant topic, given the population of people here, presented in a more expert and compelling way. Okay, so I personally am going to give me a bad toupee and an 80s style mustache, and I'm going to fool it.
Keep it just for that.
Okay, one last round of applause for Steph. Thank you so much. Okay, thanks everyone. Look for next month.